Hey everyone, welcome to the Road to Continuous Deployments. I'm Swanand. I'm currently the CTO at CoLearn, and primarily I've been a backend engineer for practically all my life. And this talk is an experience report of what we've been doing at CoLearn for the last 1 year, what has worked for us, what has not worked for us. And it also goes way beyond just the last 1.5 years. It's kind of like my thesis of how good engineering cultures should be, how a good engineering team should run, and what are some practices that are beneficial over other practices. Cool. So without further delay, let's dive into the talk. Like I said, the talk is about continuous deployments, which is a slight pun on a very popular philosophy called continuous delivery. And this is an experience report. This is me. I run the meetup for Bangalore Ruby. I've been doing that for about 15 years. I have this website where I blog occasionally. I also run a SQL workshop for intermediate developers to reach the advanced level. So the background of this talk, to set the proper context of when all of this is happening, I want to give a little bit background on the team size, on the company, a number of users, product, etc. We'll take a few minutes for that, and then we'll dive into the actual main material. So we are an education platform for K-12. K-12 typically means school-going students from grade 1 to grade 12. So we are an education platform for them. At the moment, we're in Indonesia, and our primary mode or primary product is live classes. We believe live classes where a teacher is present and interacting with students is the better way to go over, say, recorded content. And then we also have a pretty nifty AI-powered homework help app where students can take a photo of a homework problem they are stuck on and upload and send it to us, and we send them a video solution, which is built on a machine learning-based platform. So 1 year ago, we were roughly here. Our code bases were about 8 months old. We had a service-oriented architecture, Node.js-based backends, React-based frontends, and we had an app, Android and iOS app written in Kotlin and Swift, which are the native technologies. Fast forward 1 year later, or today, the code bases are obviously 1 year, 8 months old. We still have the service-oriented architecture. Much of our backend has shifted to Rails and Django. We have maintained React on the front end. We have maintained native Android and iOS, but a Flutter rewrite is in progress. More on Flutter later in the talk. Today's talk is primarily about backend engineering and front-end engineering. I'm intentionally not diving deeper into mobile. Our mobile team is working on a separate version of this talk where they'll talk more about Flutter and the mobile. So when your company is in an early stage, pre-series A, seed stage, or pre-PMF, MVP stage, often you do not have the time to put in engineering rigor. And so the code and software system that you inherit, they often come up without a lot of engineering rigor baked in, right? And so that's what we inherited, right? And then there has been the other constant factor of growth for us has been the team. We grew from, in that whole 1 year period, we grew from 20 to 35 in engineering. Our product team went from 4 to 12. Our design team went from 2 to 10. So roughly around 20, 25 members strong to we are somewhere around 50, 60 members strong. And so that also is a common parallel context to this talk. Apart from growing our user base, we're also growing in our team. So who's the target audience for this? Typically product engineering teams, founders, CTOs, CPOs, early stage, or VP of engineering, or software developers who are looking to really upgrade their understanding of how engineering should run. And then also product managers who are working with engineering teams all along. But it's not limited to this. If you're not one of these, don't worry, the talk is still relevant to you. I want to go a little bit into why CD. The idea behind CD is popular enough. Continuous delivery is a popular enough concept these days. And assuming you're coming to this talk, you're already familiar with what CD is. And I'll assume that you are fairly bought into the ecosystem. But despite that, humor me for a little bit. What do you think this is, this picture, in your opinion? Uh, this is public transport, right? People are waiting for a bus to come, and then they want to get somewhere, and they're using bus. So consider these two scenarios. There is a bus that goes every hour, right? It can fit a lot more people, and more people can move around. Versus there are these smaller cars or jeeps which run every 5 minutes, right? So if you compare those two, like in your opinion, which one is better? Every 1 hour or every 5 minutes, right? If you do some back of the envelope calculations, it'll turn out that every 5 minutes is actually a little bit better, in terms of the people who want to go from one point to other point, right? But let's go one step further, right? Consider this. How about this, right? There's a conveyor belt. If you've been to like a pretty big airport like the Heathrow or Dubai airport, they have these giant conveyor belts where you just hop on and you walk. You don't even have to walk. It just takes you to the other end of the hallway. And if you stretch this metaphor a little bit out to public transport, then imagine if you just had to step out from your house into like a conveyor belt which is going all over the city. You just hop on, get where you want, and you hop off, right? Now this metaphor can't be stretched further, but that's the idea behind continuous delivery, that you have a continuous flow of your software and your changes, and every small change that you make to your system, you're deploying it to production. And to come out of the metaphor back into the software world, the main idea is that we have to find and surface bugs faster. We want repeatable and reliable delivery of our software to our users. And we also want to mitigate some of the risks of putting software out there. These are risks like critical bugs, somebody losing money, or life-threatening situations, or even like people having a bad experience, etc. Right? And so when the costs of doing something are non-linear, they increase polynomially exponentially with each added weight. What we want to do is keeping it small, right? Because if you look at the failure hierarchy of any change management process or any software development process, at the top, the worst of them is failure, system failure, which is, for one, a very bad experience for users and then also very costly. Then a level below, you have major failures or major repairs, which means like your system hasn't failed, but you have to put in a lot of money and costs and effort to actually get some repairs done. Then below that, you have minor repairs, which they still cost money, not as good as not having any repairs, but still better than major repairs. And then finally, preventive maintenance, right? And you see this metaphor in other parts of life, like car, for example. The reason we give our car to a service center every 6 months is that we want to avoid failure and major repairs from time to time, which can be like fairly costly. Like if you add up the cost of the servicing of your car over, say, 6 years versus having to buy a new car in 6 years, they're not comparable. Buying a new car is like way more costly. And so preventive maintenance is what the main thing is. We want to build software in a way that resembles preventive maintenance. And what are the results? Well, here's a fairly accepted outcome of continuous delivery, which is improved velocity. Teams definitely iterate faster when you're in a CD mode. You build a better product through rapid iterations. Mere fact that you're deploying to production every day puts you in a mindset of iterating and running experiments faster, and that helps you build a better product. And then again, improved code quality, reliability, architecture, a lot of ancillary benefits in your engineering, product, and design layers. So what's the catch? If CD is so good, why isn't everyone doing it? Number one is that it needs a lot of rigor, which is not always possible for every team. It does need to or need you and your team to put in a certain amount of upfront thought and upfront planning to make it attractive and make it actually possible. Also, for moving from a non-CD compatible system to a CD compatible system needs a lot of careful time and execution, which not a lot of team have. And then it does incur slightly higher short-term costs. These costs are actually quite low compared to the longer horizon. And when I say long, I typically mean 6 months to 1 year, 2 year. I don't even mean like 4 years, right? 2 years ago, nobody knew there was going to be a pandemic and the world will shut down. So nobody knows what's going to happen beyond 2 years. But you do end up paying the higher short-term cost in the 3-month horizon typically. All right, with that, I want to stop selling CD and I want to start talking about how and why we're doing it. So the methodology breakdown is like this. We have the 3 Ps, as I call them: pair programming, playbooks, pipelines, right? And then we have, I'll ask you to dot your I's: instrumentation, infrastructure as code, immutable infra. You can cross your T's. That means TDD, testing, trunk-based development, your feature flags, what the F's. Don't get any funny ideas. Big O's, observability, on-call rotation, etc. Right? But these are just fancy ways of saying these things. If you truly look at each of these things that I spoke about and you rearrange them a little bit, what you'll find is that pairing, test-driven development, trunk-based development, and on-call rotation add up to what I call as building the rigor in the team. It adds a certain amount of rigor that you need. Testing, instrumentation, testability, observability, feature flags, all of these combine to give you an ease of verification for your software, fundamentally answering the question that what you are doing, is it actually working or not? Is it the right thing or not? And then finally, reducing operating friction. Infra as code, immutable infra, pipelines, playbooks, they all come into that section. What you want is you want your team to be focused on the core problem that you're solving, core business value, core product value, core user value. You don't want the team to be unnecessarily focused on inter-team communication, infra, friction, all of that. You want them operating at their best, doing what takes your product and business and users forward, right? And so all of these things make that operating friction go down, enabling your team to move faster. Ultimately, it really does come down to this central idea, which is building a sustainable culture of shipping great product, right? You can create a high intensity short-term culture, but then it's not sustainable, right? Or you can create a relaxed culture which is sustainable but not high intense enough. The idea is to find a golden middle that just works. So to summarize the methodology, we have 3 sections: build rigor, make verification easy, keep your operating friction low. Let's look at the first one, build rigor, or as I like to call it, putting the engineering in engineering. This is a term I derived from classic engineering and academic disciplines, right? Build rigor is, like we saw earlier, broken down into 4 parts: pair programming, TDD, trunk-based development, and finally on-call rotation, right? So first of all, pair programming. Why did we pick pair programming? Why did we think of pair programming when we were trying to build a CD culture? Honestly, I don't want to go into why first. I'm going to show you the results first, right? Let's look at the results. What happened 1 year down the line? What are we observing after doing pair programming consistently for a year, sprint after sprint, right? Number one, consistently high eNPS. I measure every month. Our eNPS has never fallen below 73, and the max has been 87. The industry standard engineering team eNPS is somewhere between 30 and 40. We're doing like way better than that, right? Team members routinely tell me that they are grateful to work in this team and they're having a great time of their life. People have built better connections. They build better work relationships. A lot of the pandemic induced remote anxiety has gone down. People do not feel isolated working from the home alone, which is a big factor in a pandemic induced remote work from home, is that your social circle or your social part of your life is sort of cut off from you. And all that is in front of you is house, family, and your work. And then people feel isolated because they're not used to working in this kind of situation. And so pair programming has been a major factor in our team overcoming that. And I'm not saying this is coming from my team members through routine one-on-ones, etc. Right? Not just the employee morale and culture, our velocity has also consistently gone up. Our pairing velocity and non-pairing velocity are on par, which means having fewer delivery streams because of people pairing has not affected our velocity. In fact, it has gone up. Here are some charts from Jira velocity charts. If you see the green line, that is the number of story points we delivered uh, throughout various sprints. If you see, take a glance at it, you'll see there's a consistent upward trend going up, 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 up. Ignore the last two bars. Those are December and January, where we had lots of holidays and Omicron was running wild. And so 70% of my team was off because of COVID. But if you ignore those last two, where we took a hit, there is a consistent upward trend. So that's velocity going up, right? Despite doing fewer delivery streams. Fast onboarding. We ship code to production in week 1. Any new joinee who comes and works and starts with our team, within week 1, they push code to production. And our weekly active users are somewhere around 1.5 million, sometimes 2 million. Imagine coming and joining a new team, you're writing a code and pushing it to production, and within 4 to 5 days, 1.5 million users are using the code that you write, right? That kind of iteration speed is irresistible to a lot of people. We are on board new languages, frameworks in a sprint or two. We are primarily Ruby driven, but 3-4 months ago, half my team was completely new to Ruby, right? And now people who are completely new to Ruby are sending upstream patches to open source code bases within a couple of sprints. All of that is happening because there is a very strong pairing and mentorship culture. I'm not saying that pairing is the only factor contributing to this, but it is a major factor because we measure constantly, right? We have done a bunch of internal transfers with zero friction, right? Just last 2 sprints ago, 2 of my team members moved from one team to another, right? And they're already contributing to the tech specs. They're already contributing to roadmap. They're already pushed stories out into production. And so the whole internal transfer has been like practically zero friction. Our tech debt is consistently low. On all the greenfield projects, we've assumed practically zero tech debt. Code quality has consistently gone up. And again, we measure, right? All of these things, I have data, we measure, and we keep a track on how we're doing, right? Our documentation quality and quantity has gone up. People are writing more Jira stories. People are writing more Confluence documentation, more Google Docs, and the quality has gone up, right? Architecture has been flexible. And so all of these are uh, sort of representations of a strong engineering driven culture. And so back to why did we pick pair programming? Well, a mix of prior experience, established research out in the market, and then some first principles thinking about all of these things like remote, pandemic, culture propagation, all of these things, right? So quickly running through the research, pair programming has shown to do these things: improve design quality, reduce defects, reduce staffing risk, etc. I don't want to go into details of these. There's a paper here called Costs and Benefits of Pair Programming by Alistair Coburn and Laurie Williams. I'll link to it in the show notes and you can go read it. There's a lot of research beyond this paper as well, right? So now how do you do it, right? Let's say you are convinced and you want to do or start pair programming in your team. How do you go about it? So the idea or the advice that follows is like this. One is use the driver navigator pattern. For any idea to go from the navigator's head to the code, it must go through the driver's hands. This is the key idea behind pair programming. If two, let's say Alok and Swanand are pairing, then for an idea to go from Swanand's head to the code, it must go through Alok's hands, right? And that is the key, and then vice versa, right? This is the key idea behind driver navigator pattern. It is the single biggest and the most effective pattern in pair programming. But here's the thing, when you're pairing in a driver navigator fashion, do not have fixed roles, switch roles every hour or periodically, right? Let's say right now, Swanand is the driver and Alok is navigator. Maybe 1 hour later you switch, Alok becomes driver and Swanand becomes navigator. Senior junior here is immaterial. Often people are driven to think that the seniors must be navigators and the juniors must be drivers, but it's immaterial. Both get to play both the roles. That is how your ideas and exchanges and mentorship happens. And then you want to avoid, when pairing, you want to avoid giving line by line instructions, right? Instead, you want to convey the general idea. Like imagine this. Let's say you're helping somebody chop the onions. You don't really say, oh, cut the top off, now cut the onion in half, now do slices here, now move your knife 90 degrees and then make an incision here. Instead, you only say make medium sized dice onion, right? Or you want say thin slice, thick slice. You're giving high level instructions and you're assuming and you're depending on the other person's training and experience to know what exactly that means, right? And in some cases, let's say if you truly want somebody to learn how to chop onions, you may actually show them how to do it, or you may give them more specific instructions. But in general, you will assume that they also know how to do it. You can just tell them how to do it better, right? The mentoring happens during both driving and navigating. Seniors have to take on that additional responsibility of mentoring juniors. There's an implicit assumption and requirement for all the seniors. Now, remote pairing I have found to be more effective than in person because of the natural role selection, right? If whoever is sharing screen becomes a driver, the other person becomes a navigator. Quite natural, because the navigator is going to look at your screen and tell you, hey, do this, do this, do this. Whereas you are in control of your computer, and then you're just going to go about it. So that role selection fits naturally with remote work. Mobbing also becomes incredibly easy. Mobbing is where there are more than two people working on the same problem at the same time, an extension of the same pairing metaphor. Mobbing again is easy. Just join a Zoom call or the Google Meet call, and you're in the group, right? Switch pairs every single sprint, right? Avoid pairing silos. You want everyone to pair with different people at different points of time. This kind of pairing is called promiscuous pairing, where people pair with different people. Uh, Creating pairing silos stalls culture propagation, which is exactly the opposite of the effect that you want to have. Often, some pair is going to do really, really amazing work, right? And they'll be really good at this. And you'll be tempted to let them continue working in that fashion, but switch them anyway, right? Switch them. And exhaust senior junior pairs first because of the implicit mentoring angle that I spoke about. If you have, let's say, 3 seniors and 3 juniors, then you want to do the senior to junior pairing first. You have, let's say, how many 6 combinations on to exhaust. Then you go on and do senior senior or junior junior pairs, because by then everybody will be familiar enough with the technology, with the code base, etc., for the seniority juniority to not come into picture. When the sprint ends, you swap your pairs, even if there's work in progress, right? This is a very effective litmus test of the team's communication and coordination capabilities. If you want to keep a sense of ownership, you can retain one of the pair to be the owner of the user story that you're working on, but you swap the other one out. This, like I said, this is a great litmus test to see whether you're actually doing well or not. The developer experience in a pairing culture is quite critical. You want the engineers in your team to let you know how they're doing, whether it's working for them, whether it's not working for them, what are the challenges routinely, right? Let the pairs figure out the balance between solo working and deep focus work. Sometimes people are like, just Swanand, leave me alone. I want to work on this. I'm in my zone. And at that time, you do not want to enforce pairing on them, right? But often when you're writing production code, pairing is important. So whoever the pair for that sprint is, you want to let them figure out the balance between. We have like a case where there's one person is an early morning person, the other person is a late night person, right? And so for them, the number of overlap hours they get are few. But we haven't really created any rules, right? We let them figure out what works and what doesn't work for them. Have routine health checks with your team about how they're doing. Like maybe send out Google surveys, have conversations. Let pairing be a feature in the one-on-ones that happen between managers, happen between peers. All of this together is going to give you constant feedback about your pairing culture, and also going to give you the yield that we spoke about earlier, right? Here's something that I want you to think about. Have you ever been in a commercial flight, let's say Indigo or Vistara, where there were only one pilot? I'm willing to bet no and never. There are always two pilots in a flight. And the banter that happens between the pilots, the captain does not say to the first officer, oh, turn this knob 15 degrees, press that button, now push that lever. The captain is going to say, reduce the elevation by 1,000 meters. That's it, right? And then the other person knows what to do to reduce the elevation. Or they're going to say, turn 15 degrees, right? And that's all they need to tell. They need to only give high level idea, or need to convey only high level ideas, right? And then the other person already knows, they've been through training. They're also a pilot themselves, and they know what that means. And so whenever you think about pairing, I want you to think about this metaphor quite a bit. So to summarize pairing, use Driver Navigator. very useful and effective pattern. Switch pairs every sprint to not keep silos, and then have routine health checks with the team. Right. With that, we are coming to the end of pair programming. We're going to move on to TDD, test-driven development. Again, like, why did we pick test-driven development? Honestly, I do not want to go dive deep into why TDD. This is a topic that keeps coming up for discussion. You go to any meetup, any Ruby meetup, any Python meetup, and some or the other person will be talking about TDD. There'll be some talk every few months, some blog post. So it's a topic that has been discussed way too many times, right? So what I do want to tell you is that I'm going to leave you with these two thoughts. Number one is that TDD improves testability, unquestionably so. There's plenty of research, plenty of experience behind that. This benefit is alone enough to embrace TDD, right? But that's not all. TDD also forces you to think in terms of specifications and thereby improving your product thinking, right, along with your code quality. So is TDD suitable for every single software project? Of course not. If you're building like a multi-pass compiler or writing a very complex spaceship code, maybe TDD is not the right way to do. You have different constraints to think about. But if you're a product engineering team building a product, say a SaaS product, B2C, EdTech, whatnot, FinTech, then you are dealing with a specification-based product where TDD really does help, right? And so again, what I want to do is I want to show you the effects of using TDD for a year in production consistently, sprint after sprint. The first and the most important observation is that there is a consistent, clear, significant uptick in quality of code wherever TDD was followed versus wherever TDD was not followed. When I say we have been practicing TDD, let me be honest, some teams have not been doing it from time to time, right? Are we doing it 100% of the time? No, we're not. I trust my team enough so that they know when to do it versus when not to do it, right? Sometimes somebody's in a hurry and they refuse to do it. Sometimes somebody just wants to quickly do something, or they want to write throwaway code, so they don't always do. And so our consistent observation is that the quality in code and architecture and everywhere is better when TDD was followed versus it wasn't. And in this particular case, legacy code bases and greenfield code bases do not matter. This observation stands for legacy code bases that we inherited or greenfield code bases that we built from scratch. Same observation. And then TDD and pair programming are two incredible force multipliers for each other, right? They feed into each other and create a really strong positive loop. TDD works great with pairing and pairing works great with TDD. So if you do both of them and if you do both of them right, that alone is going to like 5x, 10x your team, team productivity, effectivity, or effectiveness, quality, all of that, right? And so these are the three very strong observations that we have about our own team and also like other teams that we've been talking to. So how do you do it? How do you create a really nice and strong test-driven development culture? Well, step number one is you want to have senior engineers in your team who are experienced in TDD, right? And any guess for step two? Like I'll take a pause and let you guess what step two would be based on whatever I've spoken so far. Yep, you're right. Step two is pair programming, right? You have a few people who are really good at TDD, senior engineers. After that, you just put them, in pairs. As and when they're pairing with other people, your culture, TDD culture, is going to propagate towards the whole team. And all the members who are not used to TDD or completely new are automatically going to see another person in action, work with them, and they're going to learn faster than any book or any course can, right? But let's say, what if you do not have a single person in your team who actually understands test-driven development? What do? In that case, the answer is quite clear. You go classic. There are some classic literatures out there. Ken Beck's book, David Kelemsi's books. Ken Beck wrote this famous TDD by example book. A great read, perfect start if you want to learn how to do TDD. David Kelemsi has RSpec by example. Again, amazing book that talks about TDD and BDD. Great book to get started. Or you can arrange a workshop. A lot of people from good premium consulting companies like ThoughtWorks, Pivotal, they routinely do workshops on TDD. So arrange one for your team and use that as a starting point. So that's the end of test-driven development. I'm going to go to next topic now, which is trunk-based development. To be honest, like the uh, style of trunk-based development that we do is called scaled trunk-based development, where you create short-lived feature branches and then you put them back immediately. You just do not have a long-running branch like master stage dev or main stage dev, right? And so scaled trunk-based development is what we do. Again, why did we pick it? This is a good one. There is a lot of impedance mismatch between a long-lived branch-based strategy, long-lived branches plus PRs, versus how high trust teams operate, right? The long-lived branch plus PR strategy was created by open source teams to run their open source project. This is the hypothesis. So the reality might be a little bit different from this, but this is what generally people agree on. And it works for open source project really well, because open source projects attract a lot of contributions from non-trusted sources. Anybody in the world can send you a pull request on GitHub, right? You don't even know what their intentions are, what they want, whether they are a good coder or not, etc. Right? And in such a kind of situation, you really want to have a strong gatekeeping mechanism in place, which is what pull requests do. And however, product engineering teams do not operate that way. You only know every single person who has access to the code base, who is contributing to your code. And so you do not need to act in this gatekeeping kind of fashion. You do not need to have such a strongly enforced quality control mechanism, because you already have a good quality mechanism, which is your hiring loop, right? And so there is a little bit of a mismatch between how high trust teams operate versus how PRs and branches work. And so this is one of the reasons why we picked trunk-based development. It also builds a really nice sense of ownership with the team or the code base, right? If you are, if you break the build on dev, sometimes you're always like, oh, you know what, I broke in dev, but I'll fix it. I'll not let it go to master. I'll not let it go to stage. Versus if you only have main and you broke the build, you're responsible for that. You go and fix it immediately, right? And this sounds like a very simple, shallow excuse, but in reality, actually, it's quite powerful. It actually does help teams build a strong sense of ownership. And then we wanted to be always, be release ready, right? Not always be selling, as some people say. We wanted to be always be release ready. So what are the effects of doing trunk-based development? Same as the other, like I want to share what actually we are observing after doing it for a while. Number one is that code reviews are really fast. People are responding to review requests really fast, whether it's a pull request based code review, whether it's getting on a call and doing the code review with the person. Overall, our review cycles have gotten really short. People are pushing and merging code way faster because they're getting reviews. And reviews are less necessary because of a strong pairing culture. It works both ways, right? Both of these factors contribute to making us a very strong review process, or building a strong review process. Teams respond quicker to urgent and important bugs. Some student is not able to log into our system. There's a bug in OTP. People spot that, they're able to quickly fix it. They don't have to go into like dev stage master merge hell. They run that hotfix, they deploy, and they're able to respond to bugs faster. And this has resulted into a bunch of team members also responding faster to less critical bugs, but more important. Sometimes a bug does not seem very critical, but the engineers know that this is important, and they are more responsive to these kind of bugs. And that in some ways, trunk-based development has enabled that kind of ownership. We're running more iterations. Every day, people are merging code to master, deploying to production consistently, right? And that has enabled people to run better iterations on top of the previous iterations. Mostly everything we do is built and done better in terms of smaller iterations that build on each other. And then trunk-based delivery or trunk-based development really helps us get there. There are some negative aspects as well. Not everything is all roses. There are some thorns too. Deploying to like these dev and stage environments has become a little bit awkward because we don't have a branch that maps to dev, maps to stage. And so that has become a little bit awkward, and turnkey environments have become a necessity rather than a nice to have. Heroku or Vercel style, Turkey environments. So our DevOps team is actually now building something in-house for these, right? So again, how do you do it? Let's say whatever I showed you has convinced you to try out trunk-based development, or you've been curious about it. So how do you do it? How do you build a strong sense of trunk-based development culture in your team? Number one, have extremely fast builds. Any change that anybody makes on their local machine, they should be able to run the test suite for that particular repo in under a minute, ideally, right? Your code should go from git push to production in 15 minutes flat without without fail, without any manual approval. And this includes all the tests and all the phases of the build. I haven't made this up. Charity Majors has been talking about this for a long time. Don't listen to me, listen to her. This is something a lot of the high performing teams in the world do. There's no manual approval anywhere. You push your code to Git, it goes to production in 15 minutes flat. That builds a kind of responsibility, right? Enable running focused test cases, which means if you are writing code for a particular module, then you want to run only the tests that are related to that change on your local machine. This enables your constant ownership of code base, where you change something, you test it, you make sure your build runs, and then you push the code, then the whole build runs, right? This kind of iteration encourages everyone to think about the whole build and your trunk, your branch as a whole. Have really nice and powerful, capable development machines. Don't buy off-the-shelf, low-quality machine. ThinkPads, Apple, or high-end Windows boxes. Whatever your team's preference is, you get really nice, fast, capable machines. We are buying the M1 Pro and other like higher-end Apple laptops for our team, right? You do what works for you, but buy extremely good and capable laptops for everybody. You don't want anyone to run into these kind of friction just because they don't have a capable laptop, right? And every single dev machine must have automated and manual testing setup. Whatever system they are working on, they must have these systems set up on their local machines, and they should be able to run them, see the product in action locally, right? And then again, that if you stretch that a little bit, then they should be able to set up any dependency across the org that they want on their machine. So your machine must be capable to do all of that, run all of that. That brings us to the end of trunk-based development. Onward to the next section in building rigor is on-call rotation. Again, a very popular paradigm or popular methodology. It is, so the reason I'm not going into why on-call is because it is a fairly widely accepted industry practice. So I just want to share our observations of running on-call for a year and then move on. Number one, the process is still under iteration. Honestly, we haven't truly settled on, yes, this works kind of process. We still keep changing. We still keep experimenting, trying things out. That's still happening. We have settled on functional rotations right now. There's a prevalence in the industry to do vertical team based on calls, which means, let's say you have a top of the funnel team, then that team will do their own on call. But that's not working out efficiently for us because of our team sizes. So we're running like functional on call. Backend, there's a backend rotation, there's a front end rotation, there's a mobile rotation, etc. Because we have fewer code bases, it works for us. PTOs, leaves, unplanned, like activities and whatnot, still pose a challenge from time to time. Often, like somebody forgets that they're on call and they go off on a party or something, etc. So these kind of things do happen, and these are challenges. Sometimes people have unexpected guests, etc. And then COVID has exacerbated some of these problems. Often you have some kind of emergency that you must attend to, and so these challenges do come from time to time, and we haven't truly found a way to completely overcome them, other than just building a slightly bigger team and having more people so that there's enough buffer, right? But like I said, these are some of the challenges that we're still facing in every week, sprint after sprint. Here's a cool observation. Every single team member that has done really, really well during their on-call has also done really well in their performance review, right? Very strong correlation. Is there causation? I don't know, but there is a very strong correlation, right? Every single person who was proactive, responded to user fast, found a bug, made people move, if like reached out to different people, cross-team collaboration, whatever it is was needed for that particular on-call issue, they did that. And whoever did that really well, it's clear that their performance reviews also reflected the same kind of ownership attitude, right? Maybe there is an underlying pattern there, but I don't want to jump to conclusions. All I'm saying is there's a correlation there, right? Causation, like I said, I don't know. So how do you do it? How do you actually do and set up an on-call rotation? Again, there is a lot of advice out on the internet. PagerDuty has an extensive manual. GitLab has a manual. Uh, OpsGenie, Atlassian's on-call product, which is what we use. They also have documentation to run on-call teams. I don't want to go into that. Google's SRE book also talks about a lot of processes. So these are some of the resources you should look into if you're trying to build on-call rotation. I'll add a couple of tips based on our experiences. Number one, start with a very robust triaging process. Every on-call rotation or every on-call rota fundamentally starts at having a really nice, robust bug triage process, because not everything is a system emergency. Not everything is a problem that needs to be looked into. Some of them are like frequently occurring bugs, etc. Right? Have a playbook where all of these common problems are listed and their remedies are listed. Oh, you did not get OTP? Go look at this. You're not able to log in? Go look at that. You're not able to join the class? Go look at that. You're not able to download something? Go look at this. You will have these 5-6 different or maybe 10-15 different scenarios that keep occurring, right? Especially in B2C, consumer facing products, there are a handful few situations which repeat like a persistent boomerang, right? Oh, I can't pay for my order on Swiggy. I'm unable to, I placed an order, my bank account got debited, but the order was not placed, right? I'm sure Flipkart sees this kind of thing thousands of times in a day. And so any other B2C company, these handful few situations keep occurring again and again, again and again. And you got to have a nice playbook where all of these are listed and you know what to do when a situation like that occurs. Enable your customer support team, user facing teams to take actions, build tools so that they can do this, so that the load on your engineering on-call team is reduced a little bit. Use managed services as much as possible. Using managed services actually greatly reduces operational on-call coming from system outages, right? If you're running your own Postgres versus you're running AWS RDS, the level of reliability between those two is an order of magnitude high. So you might want to think about RDS first, right? And only when the costs get prohibitive, you want to switch about or think about running your own Postgres. Try very hard to get into a follow the sun on-call model, which means no VRs, no staying up late, no waking up early for people as much as possible. This needs you to have a time zone distributed team, which is again not a trivial thing for most teams because they don't have a very sustainable or nice writing culture. But if you do, then you can create a nice follow the sun on-call model. This helps you and your team have a better quality of life. Nobody needs to stay up till 2 o'clock in the morning or needs to get up at 3 in the morning just to support their on-call. And then again, something that the SRE books speaks about repeatedly, multiple times, every single alert must be actionable, and you got to keep adjusting your alerts until every single action is every single alert is actionable. This is a non-negotiable requirement of running an on-call rotation. That's it. That's the end of our section 1. If you want to look back, or if you look back, we spoke about pair programming, we spoke about test-driven development, we spoke about trunk-based development, and we spoke about on-call rotation. Now, every single thing that I've spoken about so far, the methodology, it has ancillary benefits that go way beyond just CD, right? So these 4 things are not only about continuous delivery or continuous deployments, right? If you're going to do all of these things, there are far-reaching positive consequences and benefits that you get out of these. But you can also run a very nice CD-driven system, right? Onward to the next section, make verification easy, or as I like to call it, the fundamental question you want to think about is, how do you know what you have done is actually working, right? That's all verification is about. And verification is something that you derive from classical engineering disciplines. And I'll talk about some of that pretty soon. We have broken down verification into 4 things. Testability. Testability is a little bit different from testing. Testability is the ability of your team to actually test out the various systems. And then testing is the act of doing that, right? Slight difference. Instrumentation and observability, big factor in verification. Feature flags, and then finally static verification, right? So let's dive into the first one, testability. Why do you want to have good testability across your systems? Well, number one, I've said multiple times earlier in the talk, testability is a core engineering principle, right? I mean, if you look at, let's say Casio, if any of you were like an engineering student, you know that Casio has these calculators, right? Or even Texas Instruments. And they have these probe points at the back. If you open the calculator, there are probe points. You can touch and connect it to like a diagnostic system. It gives you all the information about that calculator, whether it's running correctly, whether the calculations are correct, whether the display is correct, all of that, without really breaking the system apart, right? All you have to do is like just find the probe points, probe them, and you get all the signals, oscilloscopes, etc. Bridges, cars, etc. They also have these things, right? Car, often you're able to tell whether a car is working properly or not just by the sound of it, etc. Right? To be able to answer questions about your system without prying open that system is what testability and instrumentation is all about, right? I don't know if you've heard this famous joke where this ship was not working, and you know that the management was really frustrated of what to do. So they called a very old engineer, and this engineer, they went around, kept checking different places. They went around the ship, and they saw, apparently they did not do much, but they just looked around everywhere, trying to listen in, see this, that. Finally, at the end of it, they asked for a hammer. They got the hammer, and then they hit the hammer really hard at one point. At that point, the ship started working. And then when the time came for paying the bill, the invoice was like $10,000. And so naturally, the finance people were really pissed. Like, what are you paying $10,000 for? They just hit a hammer, right? So why $10,000? And so they asked for itemized bill. So then the engineer, they went and gave the itemized bill, which looked like follows, right? Hit the hammer, $1, and then knowing where to hit, 9,999. So it's really all about knowing where to hit, right? Probing the right points, understanding the system in a way that it gives you enough signals to tell you what is going on. Moving on from jokes or anecdotes, the more testable your environment is, the more people will actually test it, right? You make it easy to test, it's going to happen, right? And conversely, if you make something difficult, like make testing difficult, even the most well-intentioned team members are going to find it hard and they'll slip up. And so keeping things easily testable is not only important for the health of your system, it's also important for the morale of the team. The moment there is friction in doing something, you're going to stop, or at least you'll be motivated to stop doing it, right? Nobody likes to work inefficiently, or nobody likes to do tedious things. Not always, anyway. So again, like, what are the observations? What are we observing by inculcating this testability principle in CoLearn? Well, not having a dev and stage environment, which is very close to production, has routinely caused problems, which means there are some problems that only occur in a production environment, right? They don't occur in a testing environment. And this can be quite challenging. And you want to really get ahead of this problem and not get into a situation where your dev and stage do not really represent. Like, if your user names on the dev environment are like John Doe, ABC, Michael Jackson, etc., but in your real life you have different names, Jack Ma, whatnot, small names, big names, and then you might run into issues that you only see in production. So you cannot really predict the data that is going to be produced by your production system. And so you want your testing environments to be as close to your production as you can. Static branches that map to environments like dev stage main with a dev environment, stage environment, main environment. It seems like a really nice plus. You have a one-to-one mapping, but they're actually a hindrance because of the trunk-based development style that I said earlier, right? They create a lot of downstream problems that cause a lot of friction, merge hell, deployment awkwardness, etc. So in the beginning, this seems like a good idea, but it turns out to be like a really bad idea. Opaque third-party dependencies are incredibly hard to test. WhatsApp Business API is a great example. It's not very easy to trigger a WhatsApp message through a bot, right? You have to actually have a real WhatsApp account to test things out. And if you want to simulate a load test on WhatsApp, there's no way to do it automatically. You have to have users who are actually sending messages. So these kind of opaque dependencies are incredibly hard to test. And if you have them, you want to pay very special attention to the testability of these systems, right? Service-oriented architecture and inter-service dependencies, that immediately means your complexity is growing at a polynomial rate, right? Factorial. There are three systems that talk to each other. Then you add a fourth system, then you add a fifth system, right? The complexity increases polynomially at every point. And so again, like the moment you have these kind of systems, you want to pay special attention to that kind of architecture. Cloud native systems, AWS Lambda, Google Cloud Functions, S3, etc., RDS. These are a pain to test. You often don't need to test them, honestly, but they can be a pain to test. Like, for example, Amazon's SQS, right? Pretty hard to test. But they do offer so much instrumentation at runtime that you don't truly need to test them at development time. You just have these probe points already available, right? The teams at Amazon and Google, they've already seen ahead of the problem that you're about to face. And then that's why they offer all these probes. UIs are inherently very hard to test. Like people know that this is common knowledge, right? Any kind of UI which is meant for human interaction, incredibly hard to test. And that is why pay special attention to wherever you have UIs, right? Add probes, metrics, analytics, traces, errors, whatever it is, right? You want to add them and you want to be very aware of these things, which is what we are observing as well. All our UIs, they get the maximum attention when it comes to testability. So how do you go about it? How do you, again, like inculcate a testability and instrumentation culture? There are two main themes. Number one is development time, and number two is runtime in production. Like I said, there's a clear difference between those two. In development time, the testability is a little bit different and easier than production. You want to use TDD or anything equivalent. You want to add linters, code coverage to your test builds, make testing a first-class part of your development process. Postman, tools like Postman, are amazing. Like they have this API testing kind of facilities built in, and make great use of them. Works really well. Very powerful type systems are also amazing for testability and verification and correctness of your program. This is something that we are not doing very well at the moment, but it's a future outlook for us. We're investing into TypeScript and some of the other, like Kotlin, Haskell, some languages with higher candidate types, more powerful type systems. We're investing time and we're running experiments on that. If you already have these languages or these ecosystems in your team, make really good use of them. So how about runtime environments or runtime testing? Make really good use of the lower order environments. By lower order, I mean like dev and stage, etc. Right? Heroku and Vercel review apps are like far more powerful. Like you feel like they're only there for pull request testing, but in reality, they enable a level of testability that your regular stage and dev deployments cannot. Dive down really deep into important bugs and then see how they could have been tested earlier, right? Not just reproduce them, which is different. What I meant is how would you have, or how could you have foreseen that this bug or this kind of bugs will come? Dive down deeper into that and see if you can do anything about it, right? Add traces like especially to lower order environment, dtrace, strace, AWS X-ray, etc. They're lifesaver when you are debugging a problem. Try and build idempotent units of work. Like you have APIs, you have workers, etc. They should be idempotent, right? And then pay special attention to non-idempotent units of work. A good example is sending out emails and OTPs, right? If you call a third-party API to send an OTP, that is a non-idempotent API. It will send you the number of times you call the API is going to send you those many OTPs, right? I'm sure you've seen cases where you get like a message that your transaction is approved like 100 times from the same provider, right? So you want to avoid those kind of things. Whenever there is a non-idempotent unit of work, you want to pay special attention to that and pay like add tests and instrumentation there. Eliminate string logging completely. Like there's no such thing as a string log. Every single log event is actually a key value pair with more information about the current system with the context. So get rid of your system.out.println or console.logs. Or, uh, what you want is you want to create a key value based logging. In both environments, always test for contention. Contention means you have to think about what must happen sequentially and then does it. And then coherence is something that you want to test for again. Coherence is how much information do two systems should actually interchange or exchange or need to collect from each other. And then do they really do that? Contention and coherence together form the basis of universal scalability law. And I have recommended reading on this. Neil Kanthar's work on the universal scalability law and quantifying scalability and performance. It's phenomenal quality of work. Do read it, understand it, and see if you can implement that in your software engineering. And then Michael Nagar's release it also talks about some powerful patterns to get over these problems, right? So that's the end of instrumentation. Sorry, that's the end of testability. We want to come to a very closely related topic called instrumentation. They go hand in hand. Again, why did we pick it? Learning from other engineering disciplines. The Casio example that I shared earlier comes to mind. We want a very high velocity, but preferably not at a very high upfront cost. If you look at, say, civil engineering, there is a huge upfront cost to, let's say, building a bridge, because you cannot just destroy a bridge and reconstruct it, right? You have to consider all kinds of factors beforehand. What if there's more rainfall this year than all the last 100 years combined? What if the average temperatures are higher? What if there's more traffic than we thought about it? The wind increases, the wind decreases. What if there's an earthquake? So these are the kind of things that a civil engineer or an architect must consider before building the actual bridge, because they cannot go back once the bridge is constructed, right? And so in software, we have the luxury of not having to pay that kind of high cost upfront. And so we want to take advantage of that. And we want to create a high velocity culture without paying that kind of high upfront design cost. Because if you start spending that kind of upfront cost, you can also build systems that don't fail, right? But it's not always possible. So, and then we want to build upfront and not after the fact, right? You think about these things, go from first principles, and then make systems that work instead of constantly reacting to bugs and problems and fixing them. So what are the effects of having an instrumentation driven culture? New Relic, for example, predicts a lot of problems for us routinely before they occur. They have this anomaly detection system that really works well for us. The tech spec quality has gone high, really up in all the last few months, 6 months. We add like metrics and dashboarding right into the tech specs before writing a line of code, right? We have had our share of gofucks as well. We shipped a major feature which we worked on for almost a month and a half, which nobody used in production, etc. Right? We did not have enough instrumentation in place to tell us that this is happening. We went all classic waterfall model, build everything out, deploy it, and then nobody used it. If we had done an incremental model with enough instrumentation, we could have avoided some of that. Right? Here's an example of New Relic predicting like, oh, the traffic is not really like how it should be, and it basically tells us that error rates are spiking. Look into it. On the right is an example of our tech specs where we are adding measurements, instrumentation right into the template, right? Number of bugs has gone down, by the way. And again, like I'll show you data in the next slide. Our bug triage process is really fast and getting faster because of instrumentation. People know exactly where to look, exactly what dashboard to look at, because so many dashboards exist. And because of that, they're able to triage and find things faster. We are consistently maintaining low tech debt because people are able to surface problems, see problems in production that they can't anticipate, and they are able to take that feedback, work on it, get better, right? We measure regularly. Here's a normalized trend report for 3 factors. Number one, the blue line is team size. The yellow line is our monthly active users. And then the red line is our bug reports. These are normalized trends, which means if you look at the blue and yellow lines, they have a consistent upward trend, which means our MAUs and our team size is consistently going up. But if you look at the yellow line, is trending downwards, almost flat. Our bugs are not really increasing in proportion to our MAUs and our team sizes, right? That in the beginning, there's a spike in the red line. Ignore that. That is when we actually started measuring. We imported all our bugs from the past. And so the data there is a little bit problematic. So if you ignore July, there's a consistent flatline trend for bugs, but a consistent upward trend for MAUs and MAUs and team size, right? So that's the idea. Bugs are actually, number of bugs are going down, even if you consider per team member or per user that is using our system. So yeah, so summarizing, number of bugs have gone down, bug stash process is fast, and then we keep consistently load detected. So how do you do it? Here's my top level advice about instrumentation. Number one is have 3 levels of instrumentation: infra and systems level, code and application level, like one level above that, and then finally product and business level, right? Any kind of instrumentation, metrics, pointers to add, you have to think about these 3 things. Secondly, have at least 2 kinds of thresholds. Number one is too high and too low, something that is supposed to be some value X, but is instead like 0.1X versus something that was supposed to be value X and is now 10X, right? So you want to look at both of these kind of things. And then you also want to look at too long and too short. Something is supposed to take only X minutes, but in fact, it's only taking like few seconds. That could be a problem, right? Fast is not always good. And the other way obviously is more intuitive. Something is supposed to take a couple of minutes, but it's taking like hours instead, or a couple of seconds, but taking minutes instead. So you want both kinds of thresholds, all 4 kinds of thresholds, all 2 categories of thresholds, and keep an eye on your different alerts and parameters. Envision your product dashboards before writing a single line of code, right? When you, let's say, trying to build something, you don't want to create a dashboard after your shipped to production. You want to envision and mock up your dashboard before you write your code, right? We are running a trial with this technique called GQM. GQM is goals, questions, and measurements or metrics, where you try to break down the instrumentation of your core product using a 3-phase approach. Like you look at the goals first, then you look at the questions that represent these goals, and then finally metrics that represent these questions. Look at the Wikipedia entry. Again, lot of literature on it. Get started somewhere. Very, very useful. Coming back to the main gold medal question, how do you really know what you have built is working? This is the question that you want to constantly answer. New Relic, CloudWatch, they're your friends, use them quite well. Put all your logs, metrics, APM, everything in one place, because there's often a correlation that exists that you don't know about. And sometimes there's something in the logs that correlates with something in the metrics, that correlates with something in the APM. And if all of these things are in separate places, then you can't effectively look at this. And so you want to keep everything in one place. If it's CloudWatch, it's CloudWatch. If it's Datadog, it's Datadog. If it's New Relic, it's New Relic. If it's Honeycomb, it's Honeycomb. If it's Last9, it's Last9, right? But you want a single place where everything comes together. So that's it. That's the end of instrumentation. We're going to move on to the next one, feature flags. Why feature flags? Again, like fairly accepted industry practice. The feature flags are used in different levels of software development and product development, product engineering. They work really well with experimentation. But here's the thing, they are essential with trunk-based development, right? If you're doing trunk-based development, you must have feature flags. It's not optional. And then, like I said, if you remember the conveyor belt metaphor that I shared earlier, so the feature flags are like you're putting things on conveyor belt, but covering them up so that nobody can see them, right? So the metaphor sort of applies that way, that you're constantly shipping things. Let's say you're building like a Lego plane, right? And you're shipping it, you want to send it, but you only built a wing, but you want to put on the conveyor anyway, cover it up and send it, and keep sending packages, right? Maybe the metaphor doesn't stretch that much, but you get the point, right? The idea is that you want to ship to production as fast and as early as possible, and then hide your development branches behind feature flags, right? It works great with product experimentation. Every little experiment is a feature flag and a A/B test or something together. Now, what are the observations? We do like, here's a cool thing that happens in our team. Under development work goes to production on day one. Right now, one of my teams is engaged in a full scale rewrite. And after the initial set of business and product meetings where they understood what underlying problem are we going to solve, they've already deployed a hello world application in production, right? Day one. The total estimate for this entire project is 1.5 months, but we are not going to go to production 1.5 months later. We are going to production today behind a feature flag, right? And again, that goes back to our faster iterations, fewer iterations, or more iterations, faster iterations, uh, surfacing bugs earlier, surfacing problems earlier. Having fewer technologies has really, really helped us in standardizing the usage of feature flags across the company. We are primarily on Ruby. There's a library called Flipper, which for feature flags, it works amazingly well. And now teams are writing guides and playbooks on how to use Flipper effectively, right? Number three observation is that code gets littered with branching, right? If feature flag do this, else do something else. You have to live with it. There is no other way. That is it. Like you live with it. Simple. So how do you do it? How do you create a strong, or how do you use feature flags effectively that they actually aid you versus impediment you? Have three kinds of feature flags, same as instrumentation levels. Number one is infra and systems level. You know, the types of CPU, different types of clusters, Aurora versus RDS, etc. So you will have different decision points at a system or infra level. So you have that level of feature flags. Code level, again, very common, tied with continuous deployments and turn-based development. You have these code level feature flags. If something do else, otherwise do something else, etc. And then finally, product and business levels. These are your A/B tests, experimentation, gradual rollouts, etc. Third level of feature flags. You want all three, and a good CD compatible system uses all of these three things effectively. Not all feature flags live forever, honestly. Whenever a feature matures, you want to kill the feature flag and merge the branches or remove the branches, for the reason that you already are going to see a lot of branches out on in the runtime, in the code, and you want to reduce that cognitive overload. Whenever that feature branch is done, kill the branch, have a single, remove the branching, single linear code base. Database changes have to be 100% forward and backward compatible. You will always have different parts of your system under different experimentation, but they're all going to talk to the same database, right? Often. And so you don't want database changes that are breaking in one branch to be seen by others. So those changes have to be 100% backward and forward compatible. This is arguably the hardest part of doing feature flags correct. And then prefer SDKs, libraries, and code sharing over a centralized service for feature flags. A lot of engineers think that, oh, you know what, everybody's using feature flag. Let me create a feature flag service, and all the other systems can call that service. Bad idea. What you want is to let the feature flag live in each of the service themselves. And if there are common feature flags, those can be like environment variables, etc., or secret or service manager, secret service manager, etc. Right? Prefer code sharing over runtime sharing, right? This is a very common architecture advice, applies in feature flags as well. Finally, uh, after feature flags, the last section in making verification easy is static verification. Uh, what that means is you got to have linters quite a bit. We use linters, we use source code analysis for security tools and security related practices. Lots of metrics, like we push a ton of metrics to New Relic, to CloudWatch, and we have dashboards, etc., etc. Right? So you want to have all of these. We are exploring something. We are exploring TLA Plus at the moment. TLA Plus is a specification language designed to bring out, simulate and bring out problems of your software architecture before you actually build it. And we're doing some small focused experiments for TLA Plus. So I don't have a lot of advice on TLA Plus at the moment. This is something we're exploring. And then formal verification is something that I want to explore in the future, right? Fully verified programs, maybe using Daphne, or have like static verifiers like OCaml and whatnot. So this is something I want to do in the future. We are also looking into it at the moment. But yeah, I mean, if you already know and understand these things, like go for it and try it out and see how it works for you. Mainly what you want is the amount of so static verification again comes with a slightly high upfront cost. And so what you want to do is you want to run focused experiments and then figure out whether that experiments or that particular experiment is worth or not, right? So that's it. That brings us to the end of the second section: testability, instrumentation, feature flags, and static verification. Together, they make verification easy for your software. Like whether, again, going back to the question of whether you are doing or whatever you're doing is actually working or not, whether it's the right thing or not. That is what verification means. And these are the 4 things that we are using to make sure that it actually does work. Onward to next, very important: reduce operating friction, help team focus on the important, right? You want your teams to focus on the actual business problem and building something meaningful, as opposed to, say, working on or some internal friction, internal tools, etc. So this section is made up of 3 things: pipelines, infrastructure as code, and finally playbooks to tie it all together. So let's go look at pipelines. I'm going to cover this a little bit fast. I think this is a fairly well understood part of the whole talk. You want to have automated pipelines for every single things, right? Manual deployment, no manual deployment, absolutely, like nowhere in the system. No manual approvals anywhere, no manual configuration anywhere, right? Every single thing, data information, configuration, deployment, all of that should be an automated pipeline somewhere. And there are tools that exist in the market that are phenomenal for that. Like AWS has a lot of tools, GCP has, Azure has, Heroku, Vercel, all of these have a lot of these automated pipelines that allow you to just push your code to your central code repository and then take things from there. API service, build a pipeline. iOS app, build a pipeline. React app, of course, pipeline. If your data pipeline, well, duh, you need a pipeline for that as well. Here is the core principle: make reliable deployments a foregone conclusion, right? Nobody should even think about deployments in the company other than maybe 1 or 2 people who are actively working on making deployments better. Everybody should have the confidence that you do get push and it's going to get to production in 15 minutes, right? You want to build that kind of confidence in team. They don't even want to, I mean, you don't want your team to think about any of these things. So what do we do? Here's a cool stat. We do about 50 deployments to production per day, right? There are teams who have sprints and weekly releases, bi-weekly releases. We used to have that 1.5 years ago. Now we do production deployments about 50 times per day. Every single Git push goes to production, and we do that 50 times a day. Our slowest deployment to production is 15 minutes, and our fastest is around 3 minutes. Both of these include all the testing, right? Deployments are completely transparent. You push code and things happen, and you can look at every single thing that happens in a log, on AWS, fully transparent, which means teams can focus on product and the problems, and then the DevOps engineers can actually go and look at these things, optimize the hell out of them. Entire infra is managed from the pipeline. It's tied into the AWS ecosystem. We use this tool called CDK, which I'm going to talk about a little bit later. And then this is all centralized process where things are just managed. Here's the golden rule: every Git push to production goes to, every Git push goes to production in 15 minutes flat with no manual approval whatsoever. I spoke about this earlier. You want to continue doing that. And the way to do that is having automated pipelines. Second part of reducing operating friction is infrastructure as code. So why did we pick it? We wanted to use code to write infrastructure, right? Same quality that engineering can bring. We wanted to bring in DevOps as well. Declarative infrastructure. You write Python code and create a Redis server. We want the vertical teams, product teams, to define and manage their own infrastructure. And I really did not want them to be blocked by a DevOps team, because honestly, DevOps is an engineering team, right? They're not a support team. And also we wanted to reduce operational on-call burden. The modern infra as code tools significantly reduce operational on-call burden. They automate out a lot of things, and you pay a slightly higher cost of maintenance, but get a lot in the return. And then the DevOps team can actually focus on solving hard problems, right? and security challenges, etc., turnkey environments, centralized logging, etc., as opposed to just building infra for the teams, right? They're not a support team, they are an engineering team. So we picked AWS as CDK, and we also use that quite a bit. The CDK is basically a tool where you create and write infrastructure in a declarative fashion in using Python or TypeScript, and then it creates, right? So what are the effects? What is happening after doing all of this? Very fast turnaround. New project or new system that we want to build from scratch, it goes from 0 to production in 2 hours, right? Let's say that rewrite that I spoke about, it went to production today, 0 to, from code to production, 2 hours flat. And most of that 2 hours was like taken by uh, uh, RDS, which is like, it takes 45 minutes inside, right? This includes like load balancer, DNS, HTTPS, secrets, Docker, Redis, sidekick workers, your background workers, RDS, Postgres, all of these things. After the 2 hours, like I said, 45 minutes was taken by RDS alone, right? To bring up a brand new Postgres server takes 45 minutes. So 1 hour, 15 minutes for the rest of the things, right? Our turnaround time continues to be really fast, right? Adding new AWS Lambda to like a dev stage prod pipeline, it takes 15 to 30 minutes maximum. And 30 minutes also when it's a little complex architecture like SQS, SNS, etc. When there are dependencies, at that point, it probably takes a little bit more time, but that's also 30 minutes, otherwise 15 minutes. New Redis server, yes, write your Python code, git commit, push, 15 minutes later, you're in production. So this is the kind of fast turnaround that we are seeing in infra. And again, this allows the teams to really think hard about the building meaningful product as opposed to focusing too much on infrastructure. The infra thinking is sort of baked into the engineering now, right? The engineering team does not really have to come to DevOps running every time they have a problem. They understand infra on a deeper level. The DevOps team has spent only like 1% of their time in total on-call issues, right? They are actually working on more important things: turnkey environments, load testing setups, security compliance, performance optimizations, CPU architectures. They are doing these kind of things, and they're not bogged down by constant infrastructure needs. Our lower order environments are very high parity with production in terms of infra, because of the same problem that I spoke earlier, where not having it close to production has caused problem for us, right? Remember, better testing, this CDK and infra as code makes it possible. So how do you do it? You have to have a relentless focus on developer productivity over infra cost. Your developer salaries are always going to be way higher than your infrastructure bill, right? And that is why developer productivity is far more important than infra cost. And you want to be consistently focused on having your developers free for the things that they want to do versus the things that they have to just do out of TDM. In terms of like pure finance, it's actually cheaper, like I said, because developer salaries continue to be way higher than infra cost. And then we routinely actually, in fact, save costs on infra as well, because developers have the headspace to think about more meatier problems, right? They have the headspace to talk and optimize things and save other costs, because they don't have to really think about these things again and again, again and again. So for now, we picked AWS CDK and we picked cloud native. Combination is incredibly effective, works very well. There's tracing and observability all along. And then again, similar combinations exist with other providers too, like GCP, Azure. We are on AWS, but you don't have to be. You can be on other cloud provider, still work out, right? I'll repeat my core point: treat your infra team as an engineering team and not as a support team. It's very, very important. This is a mindset change, and this will take the longest to implement in your team. Honestly, you don't want any of your team members to be like active Jira card pushers, right? You don't want teams to operate, oh, this is the next card in the pile, I'll work on it, I'll push it to prod, I'll go to the next one. You want them to actively think about the underlying problem that they are solving, underlying value that they are adding, build something meaningful. So that's it. That's the end of infra as code. And now finally, playbooks. Playbooks basically tie everything together, and you are basically encoding or codifying the ethos of your company into a written word. And we have playbooks for nearly everything. Our product engineering philosophy itself is documented in the playbook. Mobile development, how they do Android and iOS in a playbook. Onboarding, we have an onboarding playbook. We have an offboarding playbook. Git, we are working on our playbook. Feature flags, again, there's a playbook, right? People do not have to think about how to use feature flag. They have a playbook, they can read the playbook and implement it, and they routinely change. All the playbooks are constantly updated based on experience and feedback, right? We have templates for nearly everything: decision records, new code repositories, PRDs, user stories, interview problems. We have templatized everything. This helps team, like basically this helps decision fatigue, right? The idea is that we are codifying your frequent decisions, and so people don't have to take those many decisions when they're acting. It also improves compliance throughout the team through written procedures. You don't want outliers to do something off and create problems on the screen. If somebody is displaying outlier behavior, then that should be very intentional uh, and meaningful, because they want to do so, not because they don't know how to do it. And then again, we encourage participation by making all the playbooks open and editable to everybody. It's all audited, discussed, updated. So that's it. Pipelines, infrastructure as code, and playbooks. That brings us to the end of this section. And as a result, this is the end of the talk. So the summary is that continuous deployments are good for you. That's the rationale, right? You want to have a good buy-in from different stakeholders in your team. If you're not doing it, trust me, you are playing it the hard way. Not doing CD is the hard mode. Doing CD is actually the easier mode. At minimum, you want to think about preventive maintenance, right? And so to quickly summarize all the things that I've spoken about, you want to build rigor, use pair programming, TDD, trunk-based development, on-call rotation, make verification very, very easy, make it testable, have a testing culture, instrumentation, observability, and feature flags. And then finally, you want to reduce operating friction, right? Infra as code, immutable infra, pipelines, playbooks, etc. Remember, our goal is to create a sustainable culture of building and shipping great product, right? So that is always the bottom line. And never forget this bottom line. Thank you.